Welcome to example 3, where we'll explore the mechanism of a radial valve gear. This mechanical system is designed to convert rotational motion to linear motion, which is essential in various engineering applications. On the slide, you can see a diagram illustrating components of the radial valve gear. The crank labeled as OA rotates uniformly at a speed of 150 revolutions per minute. It is pivotally connected at point A to rod AB, which has a length of 550 millimeters. The point C on the rod AB moves along a circular path with center D and radius BC, which measures 500 millimeters. The rod BE, extending from point B to the ram E, has a length of 350 millimeters. Our task is to determine the velocity and acceleration of the ram E at the given position of the mechanism. The dimensions of the links are provided in millimeters, and the crank OA is shown rotating at an angle of 30 degrees from the horizontal. This example will help us understand the kinematics of complex mechanical systems and how to calculate the motion of different points within such systems. So these are the values that we're given, and first thing to do is to construct the space diagram using a suitable scale so that we end up having that space diagram. Then the next thing to do is to get the velocity of A with respect to O. And we do that and we get a value of 2.36 because we have the angular velocity of A with respect to O, and the dimension of OA is 0.15. Now we go ahead and construct the velocity diagram, which I'm going to explain in detail. So we take the fixed points O and D and put them in that location. We have the magnitude of the velocity of A with respect to O, and we also have the direction. We know it is perpendicular to the link AO. So we go ahead and construct that using a suitable scale. And the next link is AC. The link is AC. We know the sense, the direction of where the velocity will be. We don't have the magnitude. So we go ahead and construct vector AC, which is perpendicular to the link AC. Then the next point is from the fixed point D. We want to construct the velocity of D with respect to C. We know the direction is perpendicular to the link, so we go ahead and do that. So where DC meets AC is a point C. Now we are able to get the point B using the ratio of AC over AB equals to vector AC over vector AB. Once we do that, then we can now go ahead and get to the next link, which is link EB, and from the point B, we construct BE, which is perpendicular to the link EB in the direction shown. Now we know our slider is always moving in a horizontal direction. So from the fixed point, we construct a vector OE, and where OE meets BE is our point E. And now we can be able to get the first part of the equation, which is the velocity of the ram E by measurement. Vector OE is equals to 1.05 meters per second. We now want to construct the acceleration diagram, and the first component is the radial acceleration of A with respect to O. We already had the velocity value, and when we calculate, we get a value of 37.13 meters per second square as shown. The next component is the velocity of A with respect to C, and we measure that vector AC from the velocity diagram which we've just constructed. We get a value of 0.53. We square it, divide by 0.45, and we get 0.624 meters per second squared. The next component is the radial component of acceleration of C with respect to D. So we measure vector CD from our velocity diagram. We get a value of 1.7 meters per second. We square that, divide by 0.5, we get 5.78 meters per second squared. And finally, the radial component of acceleration of E with respect to B, measure vector EB from our acceleration diagram, we get a value of 1.93. We square it, divide by 0.35, and we get 10.64 meters per second squared. Now we are ready to construct our acceleration diagram. So I'm using the space diagram to illustrate how we use the space diagram to construct our acceleration diagram, which I'm going to explain step by step. So we pick again our fixed points, which is O prime, D prime. And the first vector we are going to construct is the radial acceleration of A with respect to O, and we do that in the direction shown. This vector is parallel to the link AO. Then the next component we are going to construct is the radial acceleration of C with respect to A, C with respect to A, which is parallel to the link CA, and the magnitude is given as 0.624. So we do this using a suitable scale, and that small value is given there. And now we want to construct the tangential acceleration of C with respect to A, whose magnitude we do not have, but whose direction we know is perpendicular to the link CA. And we do that as shown here. So for us to get the point C prime, we go to the next link, which is our DC. So we're going to construct the radial component of acceleration of C with respect to D, whose magnitude is given as 5.78, and whose direction is along the link CD. So we do that as shown. So O prime X is parallel to CD. Magnitude is 5.78. Then from there, from the point X, we are going to construct the tangential acceleration of C with respect to D, whose direction we know is perpendicular to the link CD, but whose magnitude we do not have. And when we do that, we get the point C prime. So Y C prime meets X C prime at the point C prime, and that gives us a value. That gives us a point C prime. Now we get the point B prime using the relation AC over AB equals to vector A prime C prime over vector A prime B prime. Next thing we do, once we get the point B prime, now we can be able to construct the radial acceleration of E with respect to B, and we do that as shown there. The magnitude is 10.64, and the direction is parallel to the link EB. Now the next thing is to get the tangential acceleration of E with respect to B, which we know is perpendicular to the link EB, but whose magnitude we do not have, and that is constructed as shown. Now we know that our RAM is always moving in a horizontal direction, so from the fixed point, we sketch the vector O prime E prime, and where O prime E prime meets Z E prime is our point E. So by measurement, we can now get the acceleration of the RAM E, which is vector O prime E prime, and it is equals to 3.1 meters per second squared, and that is our answer.